Okay, so the last 3 lectures will be focusing on a new system, on the neuron. The neuron is part of the neural system of organisms in the human, the brain, and all the neurons that innerve the remaining part of our body, like our muscles, our skeletal muscle, and our somatosensory surfaces, our skin, and so on. But the brevity in time will only permit us to talk about one element of this neural circuitry, namely the neuron. The neuron itself is already an element that participates in what neural systems in organisms do, namely decision making. So we have neural systems because we need to decide what to do, and we have sensory data like visual data and other data, and they tell then our motor system if we should run to catch the prey or run away from somebody who tries to eat us. And so the neural circuitry has to compute a decision and take the sensory data. Very often apple and oranges. It's not so easy that one can just compare one kind of data against a decision, but very often one has to compare things that are rather incompatible, but one has to reach a decision what to do, and on the basis of all the information one has. But at the end of the day, what neurons are doing is they compute. And this is actually getting us into a realm of biological physics that is pretty high level. So you could think of what we have done so far as describing the physical mechanism of the gadgets in the body. How the certain elements of cellular components work. You have a protein for all kinds of things. We didn't go too much into the detail what proteins do, but the kind of theory we describe, for example, in case of photosynthesis or vision, describe, a gadget. One gadget is a solar cell. The other gadget is a photoreceptor. And that's sort of one level of description we have. But when we go to the neuron, we are suddenly confronted with something a little bit higher in a way, even though there's only a gradual difference in reality. But it is basically that we ask ourselves the question, how can these physical molecular devices carry out a strategy, carry out an algorithm to compute? And so this is something abstract. At the end of the day, just like with a computer algorithm, we need a physical device that translates the algorithm into physical processes that are then communicated back to the user. But the algorithm itself is sort of a little bit of a different level. And so I just pointed out so that you appreciate that when we think as physicists about living systems, then we really meet a scenario that has a broad range of conceptual challenges to us, and the highest or one of the highest challenges is to understand the brain, to understand how the brain computes its decisions. And then further down we come, at the end we have, let's say, myoglobin, a protein that stores oxygen and needs to take it on in the lung and give it off in the muscles. And so that would be a lot more like a gadget level thing, whereas the computing in the brain would be more an algorithm thing, pretty abstract, what we ask the physical system to do. And the neuron is the simplest part of the brain, it's a unit, but it exemplifies very, very nicely the point that I'm making here, namely how you can compute with a physical system that we find in organisms. And so in order to understand that, of course, we need to familiarize ourselves quickly with the system. And so I go here now and connect my device. And so now we look at the neuron. And here we have a neuron. And so I hope it doesn't always turn off quickly. So here we have a neuron. And the neuron is an input-output element, just like any computer algorithm is. You put something in and you crank then through logical mathematical steps, and at the end you reach a result. And so here's the cell of the neuron. This is where the neuron organizes itself structurally, genetically, with the energy. And then we have here elements that correspond to input-output. And we will find out that we have here on this side of this particular cell an arborization, just like a tree has branches. We find branches here that are called dendrites. And they are collecting information. Just think of a tree as something that moves something into the soil. Of course, the other way around almost. It gets it out of the soil, but in the soil it has, of course, also the roots. So these are basically the roots of information, the dendrites, that integrate data. And these data that come to the individual neuron are actually data that come from other neurons. We have in our brain 10 to the 11 neurons, and each of these neurons has about 1,000 to 10,000 connections with other neurons. You call those synapses, where they are exchanging information. And so you have here one of the 10 to 11 neurons having 1,000 to 10,000 synapses that collect information. So this one is a part of the neuron that's very different from the other part of the neuron. So here we have integration, an integrator in a way. And then we have here a decision element that makes the cell decide in how far whatever came here is significant. And this decision element, we call it a threshold element, because the way that the signals are actually being physically collected is in terms of a voltage that is a difference of the voltage inside of the elements of the neurons, the dendrites here, and the outside. Outside we call the voltage 0, inside we call it the cellular voltage. And this cellular voltage is usually around minus 100 millivolt for a normal cell. But in a neuron, it is also around minus 100 millivolt, but it varies a lot. There is, and that's really part of the function and of the role of the neuron to play with this potential, not just to use this potential to drive it energetic processes, but also to drive it for computation. And so here we can find a variety of these potentials that are being utilized to collect signals, and then the potential arrives here, and if this potential is significantly different from a threshold value, which the cell decides is about minus 70 millivolt, if it's lower than this, then the cell says, oh, this is really a significant change that I detected over the last millisecond or so, and I say I have something to tell the other neurons, the other 10 to the 11 neurons. And the way the cell does this now is in something that is also very typical for biological systems that look from the outside as very analog and fluid and gradual, but when it comes to computing, also living systems have to be really digital, precise. You do it, you run away, or you stay. You know, your decisions have to be clear. The life plan of an organism has to be clear. I told you the example of twins that live on different continents, are subjected to different influences every day, totally random, and maybe they are in different families, but when you bring them together, they look very, very similar. And so there are many decisions that over 20, 30 years organisms made to give them their bodies, even maybe their diseases and whatever, a very particular kind of outcome. And so here this cell has this outcome that when it sends a signal, it sends a standard signal along its axon. So what comes out is absolute standard. For every neuron, it looks more or less the same. And so you turn gradual information into, through a threshold element, through decision element, into digital information. In this case, you send a signal. And that signal is just an all or nothing signal. And it can go actually very, very long. Some nerve cells in squids, for example, go all the way from the brain of the squid to the tentacles of the squid. In our own body, we have nerve cells that go all the way from the brain to our toes, often with not quite exactly one total nerve cell. There might be 2 or 3 intermediate stations so that you don't go quite the full length of your body, but you go, you know, really like on a meter length you go to reach the extremities of your body and to elicit motion there or to get input from there. So this is a very remarkable element. So we integrate, we decide, we threshold, and we signal. And that's basically what the neurons do. And now they connect each other in such an intelligent way that the outcome of these repetitive integration, decision, signaling processes is Mozart, Planck, and Socrates. All these great minds are basing their wonderful thoughts on these kind of neurons. And so it is quite an flexible and powerful instrument that these neurons are. Now we want to look at them a little bit closer. You just see sort of different kind of neurons. Here it's called, in my book here on my iPad, a thinking neuron. So this is a neuron that is integrating a lot, signaling then, and then branching out to reach many other neurons. So this is a typical brain neuron that makes many, many contacts from the input also to the output side. Here we have a neuron that goes actually to muscle. So this neuron gets some input here, goes to muscle and tells the muscle to twitch or to flex. So this is a more simple unilateral kind of neuron. Here we have a neuron that is connected with the visual system. There are actually several neurons. These are the visual receptors that we met already. They have their cell bodies here. Here are the visual receptor parts where they are light sensitive. Light comes from here, and we learned, generates some electrical voltage change here that's detected by the cell bodies, and then it goes through a series of layers of nerve cells that do a lot of computing. In our brain, actually less than in the brain of simple animals. Like in frogs, I told you, here they go to the brain. These are the ganglion cells that go straight to the brain. And in a frog, these ganglion cells go straight to the tongue to catch that fly. And the decision in which direction the tongue should go is computed by these cells. And in the human, we let the brain muse more about what we see, so we do more of the computation in our visual cortex area in the back of our head here, this area. But in many, many animals, there's very much intelligence going on here to recognize images, to interpret images, and to respond quickly to images. For example, birds have so quickly respond to the visual field that moves very rapidly through the eye of a flying bird that the bird cannot do the wing motion by going through the brain, but it goes straight here to the limbic system of the bird and tells the bird where to up and down and where to fly and so on. Okay, so we got a few of those neural systems, and here we have a typical arborization that is quite typical and a little extreme, but you see here, you see the integration this neuron is doing before it sends out an axon. So this one is, a particular extreme arborization of a neuron that really gets, literally, you can estimate, in this case, probably several 10,000 inputs from other nerve cells to turn them into decision and signaling event to other neurons. Okay, so the way they talk to each other is through synapses, and here we have a synapse.
Action potentials may arrive at the ends of axons as often as hundreds of times per second. They are shown here as a wave of sodium ions in yellow.
Let me see if it's, maybe I even get the volume up here. Let me see. Maybe I get even.
Action potentials may arrive at the ends of axons as often as hundreds of times per second. They are shown here as a wave of sodium ions in yellow and potassium ions in purple.
So here's a neuron that comes, and this is our cell that has this arborization that gets the input from other cells through the synapse. This is a synapse. And so here comes the signal, and we thought that this cell gets an electrical signal, but now it has to be turned into an electrical signal in the next cell. You call this the presynaptic cell and the postsynaptic cell, and you now have to go from the signal in the presynaptic to the postsynaptic. And that's surprisingly complicated, but mainly because you have so many communication channels, you have so many cells, 10 to the 11 in your brain, that you have to be sure that they are not doing too much crosstalk. And so you really need a specific language, and that is done through neurotransmitters, and that's why it makes it
The
here.
release of calcium ions, in green, causes docked vesicles containing neurotransmitter molecules to fuse with the synaptic membrane and release their contents.
So the signal comes, they release calcium ions. The calcium ions is a signal to these vesicles that contain the lipids, that contain inside this red stuff. These are the neurotransmitters, and they are specific for the cell. That's basically the language, Chinese and English and French and German and whatever. And so this is specific. And so when the calcium is released, this vesicle touches now the membrane here, and now you see what happens.
Neurotransmitters in red are released into a very narrow gap between communicating neurons.
So now we are full of these neurotransmitters. Now you spoke to them. You see there now these neurotransmitters are in contact with the postsynaptic cell membrane.
In this example of receptor activation, the small neurotransmitter acetylcholine binds to its receptor in the membrane, depicted here in red. That leads to the rapid depolarization of the target cell membrane.
So there's a channel, and the red guys were these neurotransmitters, and when they bind to this channel, this is a postsynaptic cell, this is synaptic cleft, the space here, then there is some exchange of ions. Exchange of ions means change in voltage, and this is how you can change the voltage. You just basically, through neurotransmitters, you change the conductivity of that channel.
The activation of sodium and potassium ion channels launches a new action potential in the next neuron.
Okay, so you saw that it's actually a very intelligent device, and by the way, all the learning we do happens in the synapse. So when you learn to play tennis, it's a very complicated process, can take a lifetime. You are basically molding your synapses to modify themselves to the visual input, to your attention, to your desires to hit the ball back, and they are then connecting your nerve cells that are ultimately connecting to your muscles in your arm and to your hand that holds a racket, so that you are getting then a good synaptic transmission between your eyes and your intentions to the tennis arm. And so that is how you learn. It's also how you learn physics. That's how you learn, how you remember a phone number. You can change the synapse mechanically just for a few seconds. And that way you remember a certain number, then after a few seconds you forget it again. And you can flatten it, and you're getting more surface, or you can make it a little more narrow, and you can make it a little wider. And so this is where all the learning is happening. It is in these connections. Here you see a little close-up view, so electron microscopy. And you see here in green the neurotransmitters. This is the axon coming from a presynaptic neuron. Here's the postsynaptic neuron. Sorry, the synaptic cleft, so the postsynaptic neuron would be somewhere here. And here you see those neurotransmitters waiting for calcium signal, so that they are then moving into that synaptic cleft. So I think here you see how the neurotransmitters look like. This one is, I think, serotonin. And here you see one where we can even rotate a little bit around. And this is, I think, acetylcholine. That's another one. And so you have quite a few of those guys there. Okay, good. So I think that's about it. And so now you learned that that the neurotransmitter, that the cell, the neuron, is is a computing device that integrates, makes a decision, and then sends a signal. And today we talk about the integration side of it, and then maybe if we still have time, we begin talking about the decision side of it at the end of the lecture next time, and then we talk about the signaling side, Okay, so now let's begin. So now I need the full light. Can somebody turn on the light, please? So the material that I showed you here is from a book that is unfortunately or fortunately whatever only available as an iBook on iPad and iPhones. Soon iBooks will also be running on Mac computer with a new operating system that's coming out. The new version of the operating system, you can also run iBook on a Macintosh computer. The book is very cheap at the moment. It costs only $2. It's a fantastic book. Apple Foundation put a lot of money in it, and the title of the book is Life on Earth. So it should be easy for you to find it, and maybe you have a friend who has an iPad. That would be at the moment the best way of looking at it, and if you have a computer, then when that new operating system, iOS 7 I think it's called, when that comes out, then iBook will also be supported by the computer, not just by the iPad and iPhone. Okay, so now we want to talk about the neuron, and the key part is that we have an inside and an outside. So this one is the inside of the neuron, and here's a membrane, and one membrane I draw thin, the other membrane I draw fat. The reason is simply that I want to do my drawing in the bottom part and not on the top part, but they're of course the same size. And now the computation of the neuron are done electrically, and that involves the flow of ions between the outside and the inside. So here we have the outside, and here we have the outside. So this is just part of the neuron. This is, one of those branches, dendrites of the neuron, or the axon of the neuron. And at the moment, it's only important the topology. We have an inside and an outside. So on the inside, we have certain ions that contribute, and the most important ions are the ions potassium and sodium. They have a certain concentration inside, and they have a certain concentration outside. And then we have other ions. You could imagine that they are equally important, but they are not. We have a chloride ions, and we have also calcium ions. The calcium ions are very, very important, but they are only important for actually signaling certain molecular events in the cell, like at the synapse, but they are not being used for the potential with which the neuron computes. So the calcium are really very good in triggering certain events, like the neurotransmitter vesicles fusing itself into the synaptic cleft. And the cell decided, you guy, calcium, you have already an important job to do. You are the signaling generating guy. You sit here on the bench when it comes to the computing. You don't do that. For some reason, which I don't understand completely, I have to tell you, is that the chloride ions are also not used a lot. I think partially I understand it. I think partially I understand. We'll tell you even in a second. But you could have imagined that you also work with chloride ions, but the cell doesn't. And no cell does, by the way. Bacteria also have a voltage difference. They don't compute with it a lot, but they just use it for energy, and they also don't do much with chloride ions there. So, okay, good. So maybe what I can, okay, I tell you they're not so important. And we will see in a moment why. Now, important is, however, that we get differences in the concentration of these ions inside and outside. And so now I bet I have to look it up that I don't say that wrong. And so we have first the ratio of the sodium ions inside to outside. And I make things a little simple so that we remember it better. That ratio is 0.1. That means that we have many more sodium outside than inside. For the potassium, it's just the opposite. And this one is 10. So there we have the opposite. Now, it looks a little odd that, the cell uses only positive ions. What can you do with positive ions? Looks like everything is neutral. You cannot generate a signal, but that's not true. You can change the potential anytime you want by just sending positive ions outside or inside. If you do that, you change the potential. Doesn't matter which one. If you send positive ions out, you make the potential more negative inside, and the other way around. And now, then you ask, oh, maybe there's something smart here, and in fact it is. Because when you want to keep this kind of concentration difference as sort of the resting state for your computation, you need to constantly put energy into the system. And now here we see immediately why this cell is really brilliant. We had enough time for it, 4 billion years. But still, quite brilliant, because the way it does it, it uses a molecule of ATP to do the following: to send molecules of sodium out, while it sends molecules of potassium in. Neutral. So when you put one out, you put the other one in. So you do not have to do any electrical work, only entropic work. You only enrich the concentration, so you have to do work there too. But you don't have on top of it also do electrical work. And so it's very smart that nature said, let's just work with positive ions. That is much easier than to pump them, because I can always take one out, the other one in. I use them just in the opposite ratio, and then I have always power to let them move. Okay. So now, to do this, however, we need a battery. And the battery needs to generate a voltage, and we call that voltage E, sodium, divided by kBt. This would be our battery. Our voltage times E would be then the energy. That would be our voltage. So E is here not energy, but it's here like our electrical voltage difference. And so here we have then e to the minus E sodium divided by kBt. And this way, we generate this difference. So we have a battery. Every cell is a battery, literally a battery that has, however, there are two batteries. Like we always have one battery when we put it in our devices, but the cell has two batteries, a potassium and a sodium battery. These other batteries, they don't do much. We can almost forget them. Okay, so that is what we have. Now, if we now look at the membrane again, so this is basically this membrane here. Then we have then here the following. I write now the conductivity for sodium, and we have a battery for sodium. That's our E sodium. We have a conductivity with potassium for sodium, and we have a battery for sodium. And we have something for the rest, mainly chloride. And here we have an E rest. Okay, so this is what we have. And now we get a current across this membrane, and the current is 0 when the system has exactly the potassium voltage inside. Then there would be no potassium current. The pump tries to get it. This would be the battery. The battery wants to keep that voltage. If there is no deviation from it, good. Same for the sodium, if this would be the internal voltage. But in general, we have different voltages. So in general, we have E minus E sodium, G sodium. That would be our potassium current then. If we deviate from it, we're getting now a current. If E is E potassium, no current. Similar for the sodium. And similar for the rest. So this one would be our current that comes about under realistic circumstances when not, that all these batteries have different voltages, when they are not all satisfied. They cannot be satisfied because the voltage of the batteries it differs. And okay, so this is our current. We can write this current as G times E minus E0. As if we have only one kind of charge. Much simpler in your head. And we can quickly see what is a G here. G is just the sum over alpha. G alpha, where alpha is potassium, sodium, and the rest. And where E0 is sum over alpha, G alpha, E alpha, divided by sum over alpha, G alpha. So if you do that, you find quickly that how it is. This is actually a very important formula, of which I will only keep this value, this one here. Because when we go to the signaling, this will become very important equation. Well, at the moment, I don't want to go there because it would be more confusing than helping us. But later, this will be very central when we come there. At the moment, maybe I can tell already. The moment these values here, I replace them by the average values. They are constant in time. Whereas when we have signaling, then the G's are actually changing in time. And now you can see what happens if they change in time. Let's say you make one of the G alphas very, very large, larger than the others, 100 times larger. Then you can forget all the others. And then you're getting here G1, E1 divided by G1. G1 goes out and you get E1. So when you make G1 the largest, E0 goes to E1. And so on. Now what is E0? E0 is minus 70 millivolt for typical neuron. And now I give you the values of E, sodium, potassium, and rest, but I don't, because what is important is not the value of these absolute numbers, but rather what is important is the values of the relative numbers, which is V, which is EK minus E0. How much do we deviate from the resting potential E0, where we don't have a net current? And if we do that, then we find that the potassium is minus 120 millivolt. The sodium is plus 115 millivolt, about the same, opposite sign. So very interesting about the same, in which direction we deviate by 100 millivolt, quite a bit. And the rest current, that tells it all, is 10 millivolts, so that's peanuts. So you can basically forget it. So it's a little deviation, but that doesn't contribute very much. It's always near the average and so not very important. So you see here we're getting differences. And so now you see what can happen if we are changing the potassium voltage. We will bring the potential down by minus 120 millivolt. If we do a maximal change, if you do a very strong sodium change, we are increasing the potential by 115 millivolt. So you see you can really play games when you make the G variable. But at the moment, no variable. At the moment, we are in the integrating part, where the cell has constant voltages. The voltage, constant conductivity. The conductivities come around to ion channels, and so we have chloride channels for these guys, and we have a potassium channel, and we have a sodium channel, and those channels are very important because they are giving rise to these conductivities. And so, okay, good. So now, however, this is not quite the full story yet, because the membrane is actually acting like an capacitance. And so because they are dipoles in the membrane, and so as a result we are getting here also, in addition to this G, E minus E0 stuff, we are getting also a C dV to dt term. And if we have this kind of situation, current cannot go anywhere else, this is just how it is, then you can do this by poking into a nerve cell a little very thin copper wire, so that the voltage is everywhere the same inside of this cell. So this is why you need really young graduate students in science, because they have very good steady hand, not like a professor like me, like I couldn't do this, but you need to have a real steady hand to put small wires into neurons. You can do that actually directly with a squid neuron. Squids have very primitive neurons that make them go fast, the signals. They make them very thick. So the diameter of the features of their neurons are about 1 millimeter. And 1 millimeter is what a graduate student can handle with a steady hand. And so you can put a copper wire in there. And then you have this situation that everywhere the potential is the same, so no current is flowing, because when everywhere the potential is the same, that means no current is flowing. And then we have this equation for the whole system. And so now let's look at the equation. The equation is dv to dt. I bring the c over here, is equal to, and now I call this guy here, I call this one here, maybe I write it a little bit like here. We have now here the capacitance, and we have here the membrane resistance, and then we have this one plus 1 over C R membrane times E minus E0 is equal 0. Sorry, yeah, okay, V, okay, dV, but I can here, of course, subtract anything like V minus here, and so I can put here now E. Okay, good. Then I call this one, sorry, I put here, you know, V minus V0, I put here E. So I had a V here, but yeah, now I call what I call V is actually my E. So let me use new notation. V0, I apologize, but sort of I'm used to that kind of notation. Notation is just notation, schmotation, you know, whatever we call it, or we call it V. Then I can subtract V0, and then I'm getting dV to dt is equal to minus 1 over C Rm times V. And though that is a voltage relative to E0, I know this. So, okay, good. And now we can solve this one, of course. This guy here, you know from the theory of electrical circuits that you do in your first or second year in physics, this is a time. The capacitance time resistance is a time of the famous circuit that you use, for example, to make yourself your own radio. And so now we are getting then V is equal to V0 plus delta V of 0 times e to the minus t over tau. So this one was our relative current or relative voltage, and then when we add here delta V to it, then it will decay. You can find quickly that's the solution of our equation. So it's okay, very nice. Now, however, we have in the real neuron, we have not a copper wire in there. We have actually the absolute opposite interest. We do not want to have in the dendrites of the cell everywhere the same voltage. We want to integrate the signals that come at the synapses. And so we want to now account for a variation in the potential along the dendrite. And so now I have to now need the whole board here. And what I do is I divide the neuron, the dendrite up into a section that I number from 0 to n. And here I have my section mu, and here I have my section mu minus 1, and here I have my section mu plus 1. And here I have the top of the membrane. I draw it thin, and here I have the bottom of the membrane, which I draw thick. And now I would like to know how these things go if I do not have the same on the left and the right side. So if I now go, then I have here my capacitance. I have here my resistance and my battery, but I leave the battery out because I always take now everything relative to the battery, to the average voltage of the battery relative to E0. So I don't need to put it then. Here, outside, I have a voltage V equals 0, so I assume I have some kind of copper wire that puts everything to 0, the voltage here. So they will know, okay, good. So now we have here this, the same element that we had before. And so here we have then C dV to dt plus G V minus V0, so I have a battery then in here. Okay, that's what I have here. And then I have here now, I have now here the possibility that I go now to the next elements. And here I have the membrane potential. I put a tilde on there, because that's the potential I have in my element. The element here is delta x long. The next element is also delta x long. I need to keep track of the delta x because my electrical properties will scale with delta x. If I change delta x, they will change. So I have to put the delta x there because I want to make delta x later small, but I have to be careful to know how these properties change with delta x. Okay, so now I have here my a resistance I call the internal resistance, and I assume they are the same on both sides. And now I come here to here I have my potential V mu, and now here I have the same situation, except I have now here the potential V mu minus 1. And here I have the potential V mu plus 1. Okay, good. So now we need to allow this current is not 0 here, but now the current can branch out here. And so we have to use Kirchhoff's law that whatever is not being balanced here, we need to balance against this node. And so the way then the equation reads is that then we have now at the position V mu, we have C membrane tilde d V mu to dt plus R membrane, sorry, 1 over R membrane tilde times V mu minus V0. And then this one is equal to, and now we have two possibilities. We have a current here. If V mu plus 1 is larger than V mu, we get a current going towards a node. Whereas if V mu is larger than V minus 1, we are getting a current away from the node. Same direction, but away. One time to the node, one time away. So one current is counting with the plus sign in Kirchhoff's law, the other one with the minus sign. So I'm getting here now 1 over Ri times, I call it delta V mu. And delta V mu is V mu plus 1 minus V mu minus V mu minus V mu minus 1. So this is a voltage difference here. The other one, first with the voltage difference here, they both induce a current, but with an opposite sign relative to the node. And so you see that you can write this one as V mu plus 1 minus 2 V mu plus V mu minus 1. Clear why I write it as delta squared. As delta looks like a second derivative. Okay, so that's what I get. Now I need I want to get this one into some kind of differential equation, and I would like to go with delta x small. So I need to know how all my quantities change with delta x. And so here I put my quantities, and so the first quantity that enters here is C tilde, and that has unit farad, F. My next quantity is R M tilde, that has unit ohm, like a good resistance. And then I have Ri tilde, that has unit ohm, like a resistance. But now I would express those through quantities that are independent of delta x. And so I know that C is proportional, the capacitance is proportional to the area of this capacitance. That is the area of the membrane surrounding the dendrite here. And now if I make this dendrite piece segment longer or shorter, then the area will increase linearly. And so what I'm getting here is, this is equal to a delta x times C bar, where this guy has the units farad over length. Because times delta x, it becomes farad, like the unit of a capacitance. Okay, so here, for the membrane, it's the opposite. Here I have the conductivities will increase with delta x. If I make delta x longer, I'm getting more conductivity, but the resistance will scale inversely with delta x. And so here I will be getting, if you can think about it a little bit yourself, this will go like Rm bar, where here we have now ohm times length being the unit of that quantity. Whereas in the internal resistance, if I make it longer, I add resistance. The resistance will now become linear with delta x. And so I'm getting omega divided by L as, times Ri bar, and this Ri bar has unit omega divided by L. Okay, good. So now I can rewrite my equation here, and I write the equation now as follows, as Cm, sorry, C, I just write it C bar times delta x dv to dt plus G, and then I have, times R 1 over Rm bar, but Rm bar was inversely to delta x, so delta x goes here, times V minus V0, and then plus this one is equal to, and now if here 1 over Ri, that's scaled like this, and then dV. Okay, so this is my equation. Now the V0, I can take V relative to V0, so I put it to 0. Voltage is relative to V0. And so then I have dV to dt is equal to, and now I'm getting, I divide by delta x, and I'm getting 1 over Cm, C bar, Ri, so I want to be really neat here, C bar Ri bar times delta V divided by delta x squared, and then minus, and then here I'm getting 1 over C R M V. Okay, and so now I can write this one. I write it here because this is now a very important equation. So now I have these new physical characteristics. They come as new constants. One is C bar times Ri, and one is C bar times Rm. Even though they look very similar, they're actually different. If I look here in my table, then I find that C bar Ri bar is equal to, now if I look here, then I'm getting here something farad divided by length. Ri is ohm divided by length. So this one is farad times ohm, which is tau, divided by length squared. So this is a time divided by length squared. And this one here is, the other one is C bar times Rm. This is farad times omega, that is time, and then one time times the length divided by length. So this one is just a time constant, namely my time constant tau. And so what I'm getting is the equation dV to dt is equal to lambda squared length divided by tau times d x squared v, because delta divided by dx squared, see, this is what I'm getting for delta v, divided by dx squared. That is just my second derivative. So I'm getting the second derivative, and then minus 1 over tau v. So now you might worry, oh, is this is not necessarily the same tau. You are right, it doesn't have to be the same tau, but I can make it the same tau because the difference I can put into the L. So I should have put in here lambda squared rather than L. So the difference I can put into the L. So this is time over lambda squared. I call it tau. This is also tau divided by lambda squared. The difference I put into the lambda squared. So then I have two constants for two new variables for two different constants. So I didn't simplify or whatever. And this is our equation, and this is a very, very famous equation. This is a cable equation that describes for the dendrite of a neuron the integration of signals. So let's solve it. So you can consider quickly that if we are defining V of t as V0 relative to the resting potential, but we will neglect it, we are smart enough to know this, plus, and now we put here e to the minus t over tau times w of x and t. If we define this new w, this new function, then you can convince yourself very quickly that this w of t and x, of x and t, obeys the following equation: dtw is equal to lambda squared over tau times dx squared w. So this factor here solves this piece, so this goes out. And you're just getting now an equation for W, which is just a diffusion equation. And if we now consider the situation in a dendrite, that we have here our dendrite, and here we had our synapse at x0 that put on a change delta V, as we saw in this beautiful picture, in this beautiful movie, then our V solution is V0 plus, and now we have delta V0 divided by square root of 4 pi lambda squared over tau, just like our diffusion coefficient D at exactly the same dimension, times t minus t0 times e to the minus x minus x0 squared divided by 4 lambda squared over tau times t minus t0 by tau times minus t over tau. So this is how our solution is. It is a diffusion solution of an ink drop that we put at V0, except that it's invisible ink. This kind of ink that after a while becomes invisible and it goes away with a lifetime tau. So if we have now our neuron that gets here all these dendrites coming, and here we have these synapses, then we get from each of these synapses a droplet of ink that diffuses with a certain lifetime until it reaches here. We can calculate, it's a diffusion coefficient, we diffuse, we can calculate what is the probability here. It's, like one-dimensional diffusion is very easy. Now we have to do cable diffusion. There are very nice computer programs that can do it. One of them actually being developed here, was developed here on the campus by people in our biology department here, by neurobiologists from our university. And so one can solve it easily. One can find out what what will be here the amount of ink. And now the interesting thing is that these synapses, they can put in positive ink, then you call them an excitatory synapse. They can also put negative ink, where the delta V is not making the potential stronger, but rather weakening it. So you can put strong positive and negative ink to now have opposite effects. So when neurons talk to each other, one says, do it, do it, do it. The other one says, don't do it, like a devil and the angel or whatever you want to call them. You have excitatory and inhibitory synapses that are talking to the neuron constantly, boo, 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 coming every millisecond comes one of these guys. And so they are talking there, sending there in a diffusive, finite lifetime manner their voltage along the dendrite until the cell monitors here. And whenever there's something is happening, the voltage goes below a certain value, then the nerve cell says, oh, let's send a signal. So the nerve cell listens to what's coming there. But now, these cells here that converge onto our neuron, they have a very strong tendency, whenever they want to act together. Togetherness is very, very important. There is an element of concertedness, because when they speak to the cell together, rum, 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 then the signal has much better chance to come through here. So the nerve cells learn to talk together to get the signal to the other cell. So concertedness is a very, very important factor. It's like voting in a democracy. You have positive or negative vote, but you have to cast your vote, and you have to talk to the other neurons. Oh, let's cast the vote together. Let's all put a positive or all put a negative vote to make these things work, to get your signal through to this point of the cell. And when the cell counts the votes, it says, oh, there was really a significant voting going on just the last few milliseconds. Let's send a signal. That is basically the computing that leads to all the brilliance that we have in our brain. And there is no other trick, really, than what I just tell you. That is the elementary computation that neurons can do. And that is described by the cable equation and by the comparison at this point where the cell simply compares a value. How it does a comparison, we are learning the next 2 lectures. And how it sends in a signal. They're actually very closely related properties. And so that we learn next time. At this point, we just learned how the passive part of the neuron that integrates signals, how that works. Passive, because here we have conductivities realized through ion channels that are not changing in time, that have a set conductivity, and with that it works. The only thing that changes in time are the synapses that are activating the cell or not, but otherwise it is just a passive transmission of voltage through the neuron. A very brilliant thing, and so here you learn how evolution uses physics like a piano. You know, like a pianist, a good pianist can express its emotion on the piano. It can give you a message, not just like the kid who said, oh, Daddy, I played, I almost made no mistake today. Very proud, very good, and you say, oh, you're very nice. But the real pianist can express emotions on the piano. And so the physicist evolutionary physics that was used here learned to use the physics to devise an algorithm that is eminently useful for the organism. Here we are talking about the highest possible organ that living organisms produced, namely the brain and the neural circuitry, that had been realized. And so you see that you can use physics not just at the gadget level, but also at the level of strategy, of computing in a more abstract sense. And that's really quite beautiful, and that's a very nice example with which we can, complete this section of the biological physics course. Thank you very much for your attention.